Section 5.2 is about the addition rule and the complement rule. Here are some key concepts for the addition rule. The addition rule gives us a way to find probabilities such as the probability of A or B. When we say A or B, this is a compound event. It's any event that combines two or more simple events. The compound event A or B is the event that A occurs or B occurs, or that they both occur. The probability of A or B is the probability in a single trial event A occurs or event B occurs, or they both occur. To find this probability, we first need to find the total number of ways that A can occur and the total number of ways that B can occur without counting any outcomes more than once. Here's an example. 1,000 survey responses are collected. The results are, as you see in this table. So we have gender, and then we have 3 different age groups. So if one person is randomly selected from the 1,000 survey respondents, find the probability of selecting someone who is male or over 65. So to do this, we need to find the total number of respondents that were male or over 65 without counting any of them twice. One way we can do this is to mark the cells for respondents who were male or over 65 and then just add the numbers in those cells. So if we look at all the cells for the male row, we've got 123, 275, and 113. Now we also need to count the respondents who are over 65. We already counted the 113 in this cell, so we don't want to add that one in again because we don't want to count anyone twice. So we're going to add on the 202 that were over 65 but female. So we're just adding the numbers from these 4 cells together, and that gives us 733. The other way we can do this is to add the total of the male row, so the 531, and we can add that to the total of the over 65 column, which is the 315. Now when we did that, we actually counted the ones in the intersection of that row and column twice. So these 113 people here got counted twice. So we have to subtract that 113 out so that it only gets counted once. So if we add those two totals together and then subtract the 113, we also get 733, which matches what we got doing it the other way. So either way we do it, we find that there are 733 responses out of these that were male or over 65. So the probability of selecting someone who's male or over 65 would be 733 divided by the 1,000 total responses, and that would give us 0.733 or 73.3%. So for the addition rule, we can think about it 2 different ways. The intuitive way to look at it is that to find the probability of A or B, we find the sum of the number of ways event A can occur and the number of ways event B can occur, adding them in such a way that every outcome is counted only once. The probability of A or B is equal to that sum divided by the total number of outcomes in the sample space. So that's the intuitive way to think about it. The formal addition rule says that the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. So this again is subtracting out the ones that would have got counted twice if we added the probability of A and the probability of B together. Now let's talk about disjoint events. Events A and B are disjoint or mutually exclusive if they cannot occur at the same time. That is, they have no outcomes in common. They don't overlap at all. So here's a picture of two events that do have an overlap. Notice we've got two circles here. We've got an overlap in the middle. So these two events are not disjoint. These two events are disjoint because they don't have any overlap. So in a situation where we have disjoint events, to find probabilities, we can just add the two probabilities together if we want the probability of A or B. If we have an overlap between the two events, then we can still add the two probabilities together, but again, the part in the overlap gets counted twice when we do that, so we have to subtract that value out in order for the overlap to only get counted once. Okay, let's go back to our example with the survey responses. Now, if one person is randomly selected from the 1,000 survey respondents, find the probability of selecting someone who is under 18 or over 65. So again, we need to find the total number of respondents that were under 18 or over 65 without counting any of them twice. So let's say that event A is selecting someone who's under 18, and event B is selecting someone who is over 65. In this case, A and B can't occur at the same time because no one can be both under 18 and over 65. So there's no overlap, and these are disjoint events. So to find the probability of A or B, we can just add the totals for the under 18 and the over 65. Since they're disjoint, we won't be counting anything twice. So we could just take the total of the under 18 column and the over 65 column and add those two together. That gives us a total of 487 responses. So our probability is 487 divided by 1,000, or 0.487. And we already talked about complements a little bit in the last section. So remember that the complement of event A consists of all the outcomes in which event A does not occur. Events A and A complement are disjoint because it's impossible for them to occur at the same time. And A and A complement together make up our whole sample space. So the probability of either A or A complement occurring is 1. Now if we apply the addition rule to this, we get the probability of A or A complement is the probability of A plus the probability of A complement, and we just said that those two together have to add up to 1. So our complement rule says that the probability of A plus the probability of A complement is equal to 1. And usually to use this rule, we turn it around. So if we solve this for the probability of A complement, we get 1 minus the probability of A. If we solve it for the probability of A, we get 1 minus the probability of A complement. So the first one is the formal complement rule. These two other ones are how we usually use the complement rule. Here's an example. Many individuals age 65 and older rely heavily on prescription drugs. For this group, 82% take prescription drugs regularly. What is the probability that a randomly selected individual age 65 or older does not take prescription drugs regularly? So the word not is a good clue that you're talking about a complement. Up here we had 82% that do take prescription drugs regularly. Now we're asking about the probability that someone does not do that. So that would be a complement. So if we let A be the event that a randomly selected person over 65 does take prescription drugs regularly, then A complement is the event that the individual selected does not take prescription drugs regularly. Now we were told that 82% do take prescription drugs regularly, so we can assume that the probability of selecting an individual in that group would be 82% or 0.82. So the probability of the complement would just be 1 minus that, so 1 minus 0.82 would be 0.18 or 18%. Here's another example. Consider the procedure of rolling a die. Let event A consist of rolling a 5. Find the probability of event A and its complement. So event A includes only one outcome, and that is that we roll a 5. A complement is the event of not rolling a 5. Since the sample space would be all the numbers from 1 up to 6, a complement, if we look at it as a set, would be 1, 2, 3, 4, and 6, just leaving out the 5. The probability of event A, where we do roll the 5, would be 1/6, because that's one simple event out of our sample space of 6 events. The probability of A complement would be 5/6. Notice this set had 5 elements in it out of the 6. And 5/6 is the same as 1 minus 1/6. So we could get the probability of this complement either by calculating it directly or by subtracting the probability of A from 1. We get the same answer either way. Now let's look at part B of this problem. Let event B consist of rolling a 2 or less. Find the probability of event B and its complement. B includes 2 outcomes, so B is the set 1, 2. So B complement is the rest of the outcomes in our sample space, so it's 3, 4, 5, or 6. The probability of B would be 2 over 6 because there were 2 elements in this set and 6 total. We could reduce that to 1/3. And the probability of B complement we could calculate by taking 1 minus the probability of B, which would be 1 minus 1/3 or 2/3. We could also calculate it directly by looking at how many elements are in B complement. There are 4, so we would have 4 divided by 6, which would also reduce to 2/3. Here's one more example. If one person is randomly selected from our 1,000 survey respondents, find the probability of selecting someone who is not over 65. So again, the word not usually signals a complement. So if we let event A be selecting someone over 65, then selecting someone not over 65 would be the complement of A. We can find the probability of event A by taking the number of respondents over 65 and dividing by the total number of respondents. So we have a total of 315 that are over 65. If we divide that by 1,000, we get 0.315. So then we can use our complement rule to find the probability of A complement, and that says we just have to take 1 minus the probability of A, so that would be 1 minus 315 over 1,000, which would give us 0.685.